Alright, so next lecture for the benefit of everybody who was absent for various reasons. Alright, yesterday we talked about intermolecular forces, so today we're going to talk about them a little bit more. And here we go. Alright, so this is kind of a recap from yesterday. Yesterday we went over how to decide if something was polar or nonpolar, and then the three major intermolecular forces that we're worried about. So when you're assigning the intermolecular forces, remember if it's a nonpolar molecule, the only force of attraction between molecules is called LDF, or London dispersion forces. Okay. If you decide that it's a polar molecule, it has LDF, but it also has either dipole-dipole or hydrogen bonding. And to figure that one out, like you had to do to figure out if it's polar, you've got to look at the structure. To be capable of hydrogen bonding between molecules, you've got to have that hydrogen atom bonded to one of those three elements, nitrogen, oxygen, or fluorine, the most electronegative stuff. And why do we care? Because your intermolecular forces are what determines what happens at phase changes, like how much energy is required. Okay? So the stronger the intermolecular forces the molecule has, the higher the boiling point and melting point are expected to be. So next we'll actually practice assigning whether something's polar or nonpolar and the forces, and then deciding which one has the greater boiling point. Okay, so we're going to do some examples of doing this. So the first thing we're going to do is we're going to compare methane, which is CH4, to water. And we're wondering which one has the higher boiling point. So the first thing when you're trying to decide this, we need to look at the structure, because without the structure, you can't tell if it's polar or nonpolar, and without that, you can't assign forces. So for methane, you would have a structure like this, because it has 8 total electrons, all the hydrogen single bonded to carbon. So what is the shape of that structure? Tetrahedral. Good. Okay. And that particular structure is one of the 6 that gives you a symmetrical structure. And since all of our substituents are identical and we have a symmetrical structure, this means that it is non-polar. Symmetrical with identical substituents. That means as far as forces, since it's non-polar, the only force it has is what? The force that everything has? Hell yeah. London dispersion forces, and that's it. Now water also has 8 electrons. Okay. What structure would it have? It's bent. And remember that bent structures are always going to be asymmetrical, which means they're always going to be polar. So since it's polar, we know it has LDF, but then it either has dipole-dipole, because it's polar, or it could have hydrogen bonding. So does the structure allow for hydrogen bonding? Yes, it does. I'll just abbreviate that HB. Since we have the hydrogen atom bonded to oxygen, it is capable of doing this. I'm going to draw another one over here. squished in there. But that is the hydrogen bonding, not the bond between hydrogen and oxygen in the molecule. That's an intramolecular force. It's the bonding between one water molecule and the next water molecule. I was trying to make those lone pairs visible. Not super pretty, but okay. Alright, so this one only has LDF, this one has LDF and hydrogen bonding, so which one is going to have the higher boiling point? Water. Water has a higher boiling point. And this matches what we would observe because methane naturally exists as a gas, water naturally exists as a liquid. So therefore, water definitely has a higher boiling point. Alright, so the next one we're going to look at, we are going to look at methanol and hydrogen chloride. Because it's only hydrochloric acid that's dissolved in water. Alright, so this is a new thing I'm introducing to you. When you see a structure like this, that you've got so many carbons and hydrogens attached to each other with an OH on the end, this is an alcohol. And instead of calling that a hydroxide, they call that an alcohol group. Because it doesn't generate hydroxide ions. So when you draw the structure for that, the formula sort of tells you what's going on. You've got 3 hydrogens attached to the carbon. Then you've got carbon also attached to oxygen. And then the hydrogen is attached to the oxygen. So if there were more CHs hanging out here, like if it was, CH3, CH2, OH, you would have the CH3 on the end, there would be another carbon with an H and an H, and then the OH part. A little bit of organic chemistry for you. Alright, so looking at that, would you say that this is a nonpolar or polar molecule? Is it symmetrical? No. So therefore it's polar. It's asymmetrical. And if it's polar, we know that it has LDF, like everything. So then we have to decide if it's got dipole-dipole or can it do hydrogen bonding. So look at the structure. Does it have this correct structure to be capable of hydrogen bonding? Yes, because we have that hydrogen attached to oxygen. So what will happen is if you have another one of these, that really positive hydrogen on another one would be attracted to that oxygen there. So I'm just going to abbreviate HB there. Alright, so now let's look at our hydrogen chloride. I put 2 again. Sorry. Did not mean to put 2. Just drawing this in. Okay, so polar or nonpolar? Is it symmetrical? No, it can only consist of 2 atoms that definitely do not have the exact same electronegativity. So this one is also going to be polar. Alright, and so it also has LDF. But since it's polar, we have to decide if it has dipole-dipole or hydrogen bonding. Does it have the structure for hydrogen bonding? Nope. It has hydrogen, but the hydrogen is not attached to nitrogen, oxygen, or chlorine. Chlorine is not included in that whole hydrogen bonding thing, so we call it dipole-dipole. because, you know, there is going to be a partial positive charge on this and a partial negative charge on that one. So the chlorine of one would attract the hydrogen of the other one. Okay, so there's attraction, but it's just not called hydrogen bonding. It's dipole-dipole. So, which one's got the stronger IMFs? Top one or bottom? The top one. So this one is going to have the higher boiling point. Okay, and that backs up with what we see in nature. Methanol exists as a liquid. Hydrogen chloride is a gas, unless it's like bubbled through a liquid and then it dissolves and becomes hydrochloric acid. Okay. All right, the last one we're going to look at is chlorine gas versus our iodine solid. Now, knowing their states of matter, because it's color-coded for us on the periodic table, makes this pretty obvious, but let's go through it. All right, our structure for chlorine. And then our structure for iodine. Similar structures in that they are diatomic and single bonded. Okay, so is this polar or nonpolar? They are nonpolar. You're supposed to remember, to make things easier on you, that the diatomic elements are nonpolar because the electronegativities are exactly the same, so they're different to zero. So it's a completely covalent bond. They totally share equally. And since it's nonpolar, that means the only force that either of them have is London dispersion forces. So now the question comes, well, which one's got stronger London dispersion forces? How do you know? Yep, it's the iodine because this one is larger. And the larger it is, the stronger the LDF is because it's got more electrons. So the iodine is going to have the higher boiling point. And again, that matches what we see in nature. Chlorine naturally exists as a gas. Iodine exists as a solid. Alright, so the next thing, we've been talking about these phase changes and that IMFs are important to that. You need to make sure that you know the correct terms for the different phase changes. You should know most of these already. So like melting and vaporization, you know what melting is. Hopefully you know vaporization is going from a liquid to a gas. Usually we just say boiling, but technical term for that is vaporization. So there's a certain amount of energy required to make that happen. And for those two phase changes, the energy has to be absorbed. You have to put the energy into it to make the phase change happen. Opposite those two would be condensation and freezing. Of course, that's going from a gas to a liquid or from a liquid to a solid. In that one, they have to release the energy. They have to lose the energy in order for that phase change to happen. And what's going on is that in melting or vaporization, it's absorbing the energy, and that energy is being used to give them more movement. Remember, the heat we see as temperature is actually kinetic energy of those molecules, and the more they can move around, the more they can overcome the intermolecular forces of attraction that are trying to hold them in place. So when they get enough energy, they overcome, they can move around more, and eventually they go to the next phase. And then the opposite's happening if you're condensing or freezing. They are releasing that energy. It's being given back to the universe. And so since they don't have as much kinetic energy, they cannot overcome the intermolecular forces of attraction between molecules, and that forces them into a more ordered phase. So like going from liquid, where the molecules can swoop past each other, to a solid, where they're pretty much locked in place. And then that last part at the bottom is very, very important. Major concept to understand, especially going into the calculations that are associated with this chapter. During a phase change, the temperature does not change because that heat energy is being used to affect the intermolecular forces, not increase the overall kinetic energy as temperature of the substance. So there is an increase or decrease in kinetic energy, but it's not reflected in the temperature because it's going towards the intermolecular forces. Alright, so a couple other phase changes we don't talk about as much. You may or may not have heard of these. Sublimation is when you go directly from a solid to a gas. And you've seen this plenty if you've ever seen dry ice, especially like at Halloween. You know, it goes directly from a solid to a gas and makes that billowing cloud that looks like smoke. It's just carbon dioxide. Another thing that goes through sublimation is iodine. Iodine will sublime. Okay. The opposite of sublimation, though, is the one you probably haven't heard of. It's deposition. And that's when you go directly from gas to a solid. Only example I know off the top of my head for this one is the formation of frost. So when you get those little bitty ice crystals all over your car and the grass, it's because the water vapor in the air that was deposited as little ice crystals. Alright, so I keep saying there's energy associated with these phase changes. We actually have terms or names for that specific energy. So for freezing or melting, it's called the molar heat of fusion. Remember, heat is just another form of energy. And it's called molar because the values are given to you per mole. So, yeah, the moles are back. Stoichiometry will be back in full effect after spring break. Just letting you know. So, you're given this value. It's a certain amount of energy per mole. And so, if you're going to get the total amount of energy, you're going to have to, you know, stoic a little bit, figuring out how many moles of stuff you have and multiply. But the other thing is that whether it's melting or freezing, it's the same amount of energy. Okay? The difference, though, is the sign that you put on it. Okay? If the energy is being absorbed, it's positive. If the energy is being released, you're going to put a negative sign on it. And it's going to be up to you, when you're doing the calculations, to know whether or not to make it a positive or negative value. Because when it's given to you as a positive value. So you have to know when to make it negative. So if the energy is being released, you got to make it negative. So same deal with the molar heat of vaporization. Again, it's a value per mole. Of course, vaporization is a little bit more obvious that we're talking about going between the gaseous and liquid states. The heat of fusion, you kind of think fusion is putting things together. So like when you freeze things, you're sticking them together into place. That's where that comes from. But again, same thing with the signs. If you're going from a liquid to a gas, you're having to absorb the energy to overcome the intermolecular forces. So it's a positive value. If it's condensing, it's going to let go of some of that energy. It's going to release. So it's going to be negative. And that allows the intermolecular forces to attract and force them into a more ordered phase. Alright, something else that you need to know, terminology-wise, is vapor pressure of a liquid. Because we keep talking about phase changes, you know, when you're going from a liquid to a gas, we talk about boiling. Well, we have to talk about what's actually going on when things boil. So, you need to know the term vapor pressure, and I try to put it in the simplest terms possible up there. But it is the pressure that's exerted back onto the surface of a liquid by some of the vapor that has been generated from the liquid, if it was in a closed container. Of course, if it's in an open container, it's not really, you know, pressing back on it. But if it was in a closed container, it would generate some pressure. Because, you know, even if something is not at the boiling point in temperature, evaporation can happen. If you've got a glass of water sitting out and you leave it there for a week and come back and check the level of the water, some of it's going to have evaporated out. You got to remember, temperature is an average of the kinetic energy. So that means within an average, you're going to have some that are below that amount of kinetic energy and some that are way above it. So it is possible that some of those molecules are going to gain enough kinetic energy at the surface of the liquid to evaporate and become a vapor. And when they do that, they provide a pressure that presses down on the surface. Why do we care about this? Well, and I did not put it on the slide, I need to add it, so you need to write it down. Liquids boil when their vapor pressure equals the atmospheric pressure. Liquids boil when the vapor pressure equals the atmospheric pressure. And we can increase the vapor pressure of a liquid by increasing its temperature. You think that makes sense, because the hotter it gets, the more of those molecules are going to be a lot closer to having the temperature needed to escape into the gas phase. Escape. Okay. So, whenever the vapor pressure finally equals the atmospheric pressure, the water boils, or liquid rather. You actually observe at higher elevations water boiling at a slightly lower temperature. Because if you're at a higher elevation, there's literally less atmosphere above you, so there's less pressure pressing down on you. You may see on like cake mixes and things like that, there are high altitude directions. That's because the water, the liquid in it, can boil at a lower temperature, and it's not, since it's got less kinetic energy, it's not cooking the food the same way it would down here at, closer to sea level. So they sometimes have to cook at a higher temperature or cook it longer. So, there you go. Last little thing, some more terminology. The word volatile in chemistry. If we say that a person's volatile, we tend to say that they're, they'll fly off the handle easily, they're unstable. Well, the idea of unstable applies here. Things that have a high vapor pressure, that means they evaporate very quickly and easily, are called volatile. So big examples of that you should know from everyday life would be like rubbing alcohol and nail polish remover, which is primarily made of acetone. They're volatile because they evaporate easily, so they're going to generate a high vapor pressure. Now, things that have stronger intermolecular forces have much lower vapor pressures because they're holding on to their molecules more tightly. And it takes more energy to break those intermolecular forces so they don't generate as much vapor. So they're going to have a lot higher boiling points because it's going to take a whole lot more heat energy to give them enough kinetic energy to go into that phase and generate enough vapor to equal the atmospheric pressure. So the more you know. Anybody still writing? No. All right, this graph. All right, this graph is a heating or cooling curve depending on which direction you're looking at it in. The way it's drawn is a heating curve because you're going from a lower temperature to a higher temperature. It is possible that you could have like the opposite curve where it would start at a higher temperature and then go to a lower one. But I would sketch this graph in your notes because on the test you're going to have to look at a similar graph and identify the different parts and be able to get information from it. So big things you need to take away from the graphs. The slanted parts, like section A, C, and E, are all where the temperature changes are occurring. So that would be heating or cooling if it was the opposite. The flat parts are where the phase changes occur. And we know that the phase changes because there's no change in temperature, but we're continuing to add energy. So the flats are your phase changes, the slants are the temperature changes. Okay? Also notice at the phase changes, it says both phases. So when you get to right here, it's a solid. But as we continue adding energy, you have solid melting into liquid until you have all liquid when you get to that point. So phase change, freezing or melting depending on which way you're going, you have both solid and liquid phases present here. Section C, it's all liquid because you're heating it up to here, which is the boiling point. And then as you add the energy, where'd my cursor go? You've got both the liquid and gaseous phases, and there should have been a little slash there. So it's liquid and gas in section D until you get to the corner where it's all gas. One other thing that's not marked on here that I would like for you to keep in your notes and write down, the temperatures. So right here, the temperature would be your melting point. So if this was water, that would be 0 degrees Celsius. So right there's your melting point. And then up here, across from that flat, would be your boiling point. So if there were actual numbers on your y-axis, I could ask you on the test, at what temperature does this stuff boil? Or at what temperature does this stuff melt? Because you're supposed to know, hey, that's a phase change, and at that temperature is when it happens. And be able to tell me what it is from reading the graph. Okay? Alright, so I already told you that stuff at the top. The phase changes are on the flats. But you do need that next thing. If you were trying to calculate the total amount of energy for that entire thing, each section of the graph represents a separate calculation. And then you would have to add them all together. And you're about to see one of those. So the phase changes have to be calculated separately from the temperature changes. So when you're going into these, if you sort of like sketch a graph of what happens, each one of those sections that were labeled, you know, A, B, C, D, E, represents a separate calculation that you have to do, and then to get the total, you add them all together. Alright, so for example, and your questions will be worded pretty much like this. It said they'd say, calculate the amount of energy required for X amount of stuff to go from this temperature to this temperature. So it's not as simple as the prompt sounds, because you're going to have to first list what happens so you can figure out which calculations you've got to do. So if we're talking about water at 23 degrees Celsius, what phase is it in? It's a liquid. Okay? So we have to heat that liquid water at 23 degrees Celsius up to the boiling point, 100 degrees. So that would be the first slant of your graph. Once we get it to the boiling point, we have to boil it. So there's that heat of vaporization. So that's a separate calculation. So that would be a flat point on the graph. And then we didn't want to stop at 100 degrees Celsius. We wanted to heat it all the way to 105. So then we have to calculate the amount of energy to heat the steam at 100 degrees Celsius by 5 degrees. So you have to do 3 separate calculations for that, and then add them all together. So the first thing we have to do is heat the water to boiling. So that's what part 1's showing you. Hopefully you somewhat remember QMCAT. Heat equals the mass times the specific heat capacity times the change in temperature. And notice I gave you the specific heat capacity there. That's not something you're going to be expected to know. Why can't we just do the whole temperature change at once with QMCAT? Because the specific heat capacity of the liquid is different from that of the solid or the gas. So we know the amount of energy it takes to heat it up to the boiling point. Notice that I'd given you 1 mole of water, and in your equation down there at the bottom, I just put the mass in grams because that's the molar mass of water. You're given the value of C, and then delta T is final minus initial. Also, I did not round that answer to sig figs because that is not my final answer. If you start trying to round to sig figs on these steps, it's going to mess up your final answer. So retain digits, round your final answer. Alright, so parts 2 and parts 3. Part 2 is the phase change, so we're using that molar heat of vaporization for water, which they gave you. Notice that it is in kilojoules, and our previous step was in joules. We're going to have to convert it one way or the other. And then part 3, we're doing Q and CAT again, but we have to do it separately because the C for steam is different than the C for water. So at the bottom, I went ahead and converted part 2 from kilojoules to joules since I already had two things in joules, and then rounded to sig figs. So the math itself is not hard. The hard part is sitting down and saying, okay, I have to calculate this, 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 and this, and then add them together. So this is just an example so that you can at least begin to attempt your homework. We're going to spend some time in class doing these and practicing them.